Alright guys, welcome back to Underground Science, and in this video we'll be looking at another example of calculating the pH, and we'll be dealing with another weak acid, and we'll be calculating the pH with using ice tables. Alright, so in this case just one ice table. Alright, so let's go ahead and get started. Alright, so we have another question here like we had in the previous example, except we're working with a different acid, a weak acid. Alright, so we have a 1.6 molar solution of aqueous nitrous acid. So let's go ahead and label this as nitrous acid. Alright, so we have nitrous acid here, and let's go ahead and identify the fact that nitrous acid is a weak acid. So we expect the Ka not to be that high and actually to be low, because the higher the Ka, the stronger the acid. However, nitrous acid is a weak acid. Alright, so we have a 1.6 molar solution of aqueous nitrous acid. So the question is, what is the pH of this 1.6 molar aqueous solution of nitrous acid? Because we know it's aqueous, let's go and write the reaction out as it's reacting with the water. Alright, so let's go and get started. So we already have it preset here, just to save a little time. So we have our nitrous acid reacting with water, it's in equilibrium, and we form hydronium and our nitrite anion. Alright, and remember it's in equilibrium because nitrous acid doesn't fully dissociate into the products. It only some of the nitrous acid will dissociate into products, not all of it, because it's not a strong acid. So what that means is that we said that we have a 1.6 molar solution to start off with, right? But then we said that we said that this is a weak acid, so not everything is going to dissociate into the product. So how much will dissociate into the products? Well, we don't know, right? So we're going to put a minus x for the change, because we know something will dissociate, but we don't know exactly how much. So we know something will decrease out of this 1.6, but it's an unknown value. Whatever will dissociate into the products will gain whatever dissociated from nitrous acid, right? So then that means we'll have to gain the same plus x amount, all right, for both our products. Now initially we have to keep in mind that there's no products formed because it's the starting of the reaction. So we actually have 0 here. All right, and remember, water is neutral and its concentration doesn't change, so we don't count water into the calculation of our pH because it won't affect the calculation of our pH value. Now that we've written this out, all we have to do is write the equilibrium section out of our ice table. All right, so let's go and do that. So 1.6 minus x, and we're going to gain whatever dissociated in the product, so it's going to be 0 plus x, which is x, and 0 plus x, which is x. Now we have to go ahead and see, well, what are we working with? We're working with the weak acid. All right, sweet. So now we have to write the Ka, the acid dissociation equation. So let's go and do that now. So the Ka is going to be equal to the products, right? So so you multiply the products, so we have our nitrite anion there, divided by the concentration of the reactants, except for water, because water is not affected, does not affect our calculation for for our pH value. Next, what we do is that we feed in values into our concentrations here. Well, we already found that out, right? Technically, we already found that out in terms of variables. If we have to find the concentration of H0 plus, well, we look at our ice table and we see that it's X. Concentration of nitrite anion is X. Concentration of nitrous acid is 1.6 minus X. So we have to go ahead and feed that in next. So Ka, our acid dissociation constant, is equal to X for our hydronium concentration, right? So let's go and stay consistent with the colors. X for our hydronium concentration. Then we multiply it by our nitrite anion concentration, which is also X according to our ice table. So let's go and write that out. Then we divide by the concentration of our nitrous acid, which is our weak acid that we see here. and I just noticed that I put HNO3 for some reason. I don't know why. Sorry about that. So it's supposed to be HNO2 because that's the formula for nitrous acid. Hopefully I don't make that mistake again, all right? So then divided by our concentration for nitrous acid, which is 1.6 minus X. So 1.6 minus X. All right, now, well, this doesn't really get us anywhere because we still can't solve for X. All right, so again, remember that the question asks, let's go and scroll down to the question. The question asks, what is the pH? All right, and we know if we're working with the acid and we have to find the pH, we know we have to do negative log of our hydronium concentration will give us our pH. So our goal is to find our hydronium concentration. All right, so let's go back up and let's work towards our goal. Next, to even get close, we have to know what the Ka value is for nitrous acid. All right, and we wrote it up here, right, beforehand. The Ka value for nitrous acid turns out to be around 4 times 10 to the negative 4. So let's go and write that out. All right, so the Ka for nitrous acid is 4, right, times 10 to the negative 4th, right, so let's go and make sure that's it, equals, and we just multiply it out, so x times x is x squared, and we leave the denominator as it is. All right, now we can solve for x, except we don't want to work with quadratic equations and all that. We want to make it simpler, right? We want to make our life easier. So what we're going to do is that we're going to assume that x is a very low concentration. All right, so we're going to assume that x is a very, very low concentration, almost close to 0. Then if we assume that, and then if we take 1.6 minus a very, very, very low number, it's still going to be around 1.6. So what we can write this as is this, 4.0 times 10 to the negative 4th equals x squared over, one sec, let me write that neater, x squared over 1.6, because 1.6 minus a very, 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 very low concentration is still going to be about 1.6. Now we can go and solve for x like a regular algebraic equation. So then we just go and multiply that, right? So we're going to have, let's write it step by step. So we're going to have 4.0 times 10 to the negative 4th times our 1.6, right, equals our x squared. Then we have to multiply this out. So if you do that, you're going to get x squared equals around 6.4 times 10 to the negative 4th. Then I'm going to take the square root on both sides, and ultimately we're going to get x equals the square root of 6.4, not 64, times 10 to the negative 4th. And if you do that, you're going to get x equals around 0.025. All right, molarity. All right, because remember, we were solving for molarity. We're solving for the concentration. Okay, and now what's x? So what do we just figure out? Well, if we go back to our ice table, remember, okay, actually, you know what? Sorry about this. Let's go back down to the problem. Remember, we said to find the pH, we have to do negative log of our hydronium concentration. So let's keep that in mind, and let's go back up. Remember, hydronium concentration is what we're looking for. If we look here, our hydronium concentration was represented by X. All right, well, let's go back. What did we just find? We found X. So that means that the value for X is going to be our hydronium concentration also. All right, and with this value of X, we can also find how much dissociated, right? How much nitrous acid dissociated by just doing 1.6 minus the X value. We can find how much nitrite anion we have, but what we're focusing on is a pH, which is X, which is so what we're focusing on is the hydrogen or the hydronium cation concentration, which is X. We just found X, right? So now we have to do negative log of our hydronium concentration. Remember, this is the equation to find the pH. This value is our hydronium concentration, sorry, I couldn't speak there. So then the negative log of our hydronium concentration, which is 0.025 molarity, is equal to our pH. And if you go and do that, you can get the pH equals around 1.6, all right? So our pH is around 1.6. So if we go ahead and here, oh, we're already here, sorry about that. If we go ahead and answer the question, what is the pH of our 1.6 molar aqueous solution of nitrous acid, which is a weak acid, we can go ahead and answer it, is that the pH is going to be 1.6. And that's it, right? We've answered the question through a step-by-step process using ice tables, or using an ice table, all right? So I hope this video made sense to you guys. This is it for this video. We may look at more examples in our future videos. I hope to see you guys in my future videos where I'll talk about more cool topics about biochem, physics, and chem. Don't forget to hit that notification bell, like, and subscribe. See you guys later, and stay safe.